We have already discussed the notion of a normal operator on on a finite dimensional inner product space. A normal operator is a linear transformation from V to itself whose adjoint commutes with the given operator. So in this lecture, we will discuss a special subclass of normal operators. They are called as self-adjoint operators. As the name suggests, self-adjoint linear operators are those operators whose adjoint is the operator itself. So let's begin by defining what are self-adjoint operators. So let V be an inner product space, be a finite dimensional inner product space, and let T from V to itself be a linear operator, and let T be in L of V. So linear transformation from V to itself. We say that T is self-adjoint if T star is equal to the operator T itself. So let's look at an example. So define T to be from say R2 to itself given by T of x comma y is equal to y comma x. So let's fix the standard basis, which is an orthonormal basis with respect to the standard inner product. So let beta be the standard basis, and what is going to be T beta beta, or will be the matrix of T with respect to beta. This is just going to be, let's see what is T of 1 0. T of 1 0 is going to be 0 comma 1, and T of 0 comma 1 is 1 comma 0. So this is precisely the matrix of T with respect to beta, and it has real entries. What is the adjoint? So T star matrix of, so let's see, T beta beta adjoint, which is the matrix of the adjoint of T, is again the same matrix, and therefore the matrix of T star is going to be 0 1 1 0, and therefore T star of x comma y is just going to be equal to y comma x, which is equal to T of x comma y, right? So this implies that T is indeed a self-adjoint linear operator by the very definition. T is self-adjoint. Okay, now let's look at one more example, rather a non-example. In fact, let's just scroll up, go to the example of normal linear operators and look at, maybe let's focus on this particular operator. T of xy being equal to T of xy being equal to y comma minus x. So example from above continued. So let me write it as a non-example because this is going to be a linear operator which is not self-adjoint. So let T again from R2 to R2 be given by T of x comma y is equal to y comma minus x. And if you go back and check the calculations involved, we actually had this with respect to the standard basis. This was just going to be equal to 0 minus 1 1 0, and therefore if you calculate the adjoint is just 0 minus 1 here in the first row, 1 0 in the second row, and that would give us that T star of x comma y is equal to minus of y comma x, which is not equal to T of x comma y, because T of x comma y was y comma minus x. This implies that T is not self-adjoint. So this immediately tells us that not all normal operators will be self-adjoint. T is not self-adjoint because this is an example of a normal operator. Normal operator, the condition is weaker. Okay, so maybe I should make a small lemma here. It's a very straightforward observation. Self-adjoint operator is normal. Self-adjoint operator is normal. And why is that the case? Well, it's a one-line proof. If T star is equal to T, this would imply T star is equal to T square, which is the same as T star T, and hence it is normal. So it's a straightforward observation to see that every self-adjoint operator is a normal operator. And in an analogous manner, when we dealt with normal operators, we will also define what a self-adjoint matrix is. So as an n cross n matrix, so let me just call it a definition here. An n cross n matrix is said to be self-adjoint if the adjoint, the conjugate transpose of A, call it A, if this is equal to the matrix A itself. So that's a straightforward definition one would expect. And in this case, the first matrix here, this is self-adjoint. However, this is not self-adjoint. Just like in the case of normal operators, we can find a relationship between self-adjoint transformations, linear operators, and self-adjoint matrices, which will be the content of our next proposition. The proof of this proposition is going to be very similar to how we would have proved it in the case of normal operators. So I will not venture into giving a proof of this. Nevertheless, it's a very important statement. Let me write it down. So let T be a linear operator on an inner product space, on a finite dimensional inner product space, and beta be some orthonormal basis. Let me not phrase it that way. Then T is self-adjoint if and only if the matrix of T with respect to beta is self-adjoint for any orthonormal basis. That is important. The orthonormality of the basis is important. Orthonormal basis beta of V. So let's call the vector space V. Yeah. I'll leave this as an exercise for you to check. This was already done. A similar proposition was done in the case of normal operators, and that's going to go through. A similar proof is going to go through in the case of normal operators. Let's look at a few more examples of self-adjoint linear operators. Or rather, now I will focus on matrices. In the backdrop of this particular proposition, we just need to focus on matrices and prove results there, which will carry forward to self-adjoint operators as well. So, next example. So, what was one standard example of a normal operator? Diagonal matrices turned out to be standard examples of normal operators, because if you look at the conjugate transpose of it, it will again turn out to be a diagonal matrix, and the product of diagonal matrix will turn out to be a commutative operation. However, we have to be a bit careful when it comes to dealing with diagonal matrices which will be self-adjoint. So I'll just write it this way. Real diagonal matrices are self-adjoint. The reason being that if the matrix has real entries, if you look at the conjugate, the entries are going to be preserved. There will be no change in the entries. And then if you look at the transpose, again it will not change because it's a diagonal matrix. So real diagonal matrices are always self-adjoint. Diagonal matrices with complex entries, where the non-real entries are not going to be self-adjoint. For example, non-example again, you look at, say, diagonal of 1 comma I, and what is going to be the adjoint of A? adjoint of A, which will represent the matrix of the linear transformation LA star, that is just going to be equal to diagonal of 1 comma minus I, because if you look at the conjugate of I, that's going to be minus I, which is not equal to A. So in the case of matrices with complex entries, we have to be a bit more careful. The diagonal matrices will not turn out to be self-adjoint. So there is an alternate term that is used to describe self-adjoint operator. So let me just write that down. A self-adjoint operator is also sometimes called as a Hermitian operator. Self-adjoint. This is a term which you can find very extensively in literature. A self-adjoint operator is also called an Hermitian operator. Is also called a Hermitian operator. So a matrix which is equal to its adjoint is called a Hermitian matrix. In also matrix an n cross n matrix A whose adjoint, let me write it like this, such that A adjoint is equal to A is also called, it's called a self-adjoint matrix. It's also called a Hermitian matrix. If we are focusing our attention on some real inner product space, then Hermitian matrices are going to boil down to something which we are quite familiar with. So in real inner product spaces, if you notice, what is going to be the conjugate transpose inner product spaces? If A is Hermitian, A is a Hermitian matrix, that would imply that A adjoint is equal to A. But what is the meaning of A adjoint? A adjoint is the conjugate transpose, right? This is equal to the matrix A itself. But what is the conjugate in a real inner product space of a matrix? So the matrix of in a real inner product space, or let me just put it, the matrix of a linear operator on a real inner product space, or a matrix A, a Hermitian matrix A with real entries. That's what this statement means. Should I rewrite it? Its context is clear. I hope it's not confusing. What this statement means is that if the matrix A is an n cross n matrix with real entries, or in a real inner product space, you consider a linear operator T, which is Hermitian or self-adjoint, and look at the matrix of T with respect to an orthonormal basis. Then A transpose will be equal to A implies that A adjoint is equal to A implies that A bar transpose is equal to A, which would imply A transpose is equal to A, because the conjugate of our matrix is going to be the matrix itself. So hence a Hermitian matrix with real entries is a symmetric matrix. However, when we are dealing with matrices with complex entries, we have to be careful, because the two notions don't coincide then. So for example, consider A to be equal to, let's say, 1 minus I 1, and let's look at the adjoint of A. The adjoint of A will be the conjugate transpose, which is going to be 1 minus I comma 1, which is equal to A. Therefore, this matrix is actually Hermitian. But if you look at the transpose of A transpose is just going to be equal to 1I minus I 1, which is not equal to A. So this is a Hermitian matrix which is not symmetric. So the distinction of a Hermitian matrix and a symmetric matrix is quite stark in the case of matrices with complex entries. However, in the case of real entries, we just noted that a Hermitian matrix is certainly a symmetric matrix as well. Let's now explore some properties of self-adjoint operators. So we have already seen that the matrix, the linear operator T, the eigenvalue of the linear operator T and the eigenvalue of the adjoint of T are related. Lambda being an eigenvalue of T is true if and only if lambda bar is an eigenvalue of T star. In the case of self-adjoint operators, we can say more, which will be captured in the next theorem. So let me write down the theorem. Let T be a linear operator on V, be self-adjoint, be a self-adjoint linear operator on an inner product space. Then the eigenvalues of T are real. So let's spend a few minutes, let's spend a couple of minutes trying to see what this exactly means. Eigenvalues of T are real. So notice that if V is a real inner product space, then this theorem doesn't say much because the eigenvalues of T are necessarily real in that case. However, if you look at a complex inner product space, even then this theorem tells us that even in the case when the field of scalars is complex numbers, if you consider a self-adjoint linear operator on V, its eigenvalues should necessarily be real numbers. Of course, real numbers are complex numbers, so there is no contradiction there. It says that it has to be necessarily real. Let's look at a proof of this. The proof is actually quite straightforward and elegant. So we know that lambda and lambda bar are the, if lambda is an eigenvalue, so we know that if lambda is an eigenvalue of T, this is true in the case of every linear operator on a finite dimensional inner product space. If lambda is an eigenvalue of T, then lambda bar is an eigenvalue of T. But we also know when T is a normal operator of T star, I said T, but it is T star. In the case of normal operator, we know more. We know that the eigenvector corresponding to lambda of T will be the same as the eigenvector as an eigenvector corresponding to lambda bar of T star. So since self-adjoint operators are normal, by one of the theorems proved in the previous lecture, we have that if V is an eigenvector of T corresponding to lambda, then it is an eigenvector of the adjoint of T corresponding to lambda bar. So let's see. So that means hence lambda times V comma V. Let's look at what lambda comma V is going to be. That is going to be equal to lambda V comma V, which by the definition of an eigenvector is equal to the inner product of TV with V. But this is also the same as the inner product of V with the adjoint of T acting on V by the very definition of the adjoint. But since T is self-adjoint, T star is equal to T, and that implies that this is just the inner product of V with TV because T star is equal to T. But this is equal to V comma lambda V. And by the properties of the inner product, this is lambda bar times the inner product of V with itself. So what do we have? We have lambda times the length of V square is lambda bar times the length of V square. So this implies lambda minus lambda bar times the length of V square is equal to 0. But V is an eigenvector, hence a non-zero vector, and therefore the length of V has to be necessarily non-zero, and therefore the length of V square is also non-zero. This implies that one of the two has to be 0 here because it is a field, and therefore lambda minus lambda bar is equal to 0, which implies that lambda is equal to lambda bar. Okay, but what is the meaning of a complex number being equal to its conjugate? That means that the imaginary part has to be necessarily 0, because if a plus ib is equal to a minus ib, that implies that 2ib is equal to 0, and therefore b is equal to 0. And this implies that lambda is a real number. So that's good. At this time, at this juncture, it might be a good idea to introduce you a high power tool called the fundamental theorem of algebra. So let me just state that theorem here. Fundamental theorem of algebra states that if you look at a polynomial which has complex coefficients, then it splits in the field of scalars being complex numbers. So let me just write it down. Fundamental theorem. That's one version of fundamental theorem of algebra. You could state it differently, but this is more suitable for our purposes. So let p of x be a polynomial over the field of scalars being complex numbers, or to write it differently, be a polynomial with complex coefficients, in complex numbers. As complex numbers. So this is a polynomial over C. Then the polynomial, then p of x splits over C. So notice that if p of x is some a0 plus a1x plus up to a next to the power n, what this tells us is that p of x will be it will be possible to write p of x as x minus lambda 1 times x minus lambda 2 up to x minus lambda n. Always, any polynomial you take, you will be able to write it as a product of linear factors. That's quite remarkable in our case, because the applications of this is of course vast. Let's see how the fundamental theorem of algebra impacts the study of self-adjoint operators. So we already know that okay, I'll just immediately state down the theorem before elaborating on that. As a consequence of the fundamental theorem of algebra, we will be able to say that the characteristic polynomial of a self-adjoint operator always splits. So let me write it down. So let T be a self-adjoint operator on an inner product space, self-adjoint operator on a finite dimensional inner product space. Then the characteristic polynomial of T. So recall that the characteristic polynomial of linear operator is basically the characteristic polynomial of one of the matrices corresponding to T with respect to some basis. Of course, this is well defined because the characteristic polynomial of similar matrices are going to be the same, and therefore a change of basis matrix will not alter the characteristic polynomial. And this theorem says that the characteristic polynomial of T splits. So irrespective of whether it is a real inner product space or a complex inner product space, this is true. In the case of a complex inner product space, there isn't much that the theorem is telling, because if you look at a complex inner product space and if you look at the matrix of T, that will be a matrix which has complex entries. And if you look at the characteristic polynomial by the fundamental theorem of algebra, that will be a polynomial. If you look at the characteristic polynomial, it will be a polynomial with coefficients from the field of complex numbers, and by the fundamental theorem of algebra, it splits. This theorem is really telling something substantial when you consider real inner product spaces, because there the characteristic polynomial will be a polynomial with real entries. Of course, you can think of it as a complex polynomial as well, and it might split, but there is no guarantee that it will split over the field of real numbers. It will be splitting over the field of complex numbers. This theorem tells us that it should necessarily split over the field of real numbers as well in the case of real inner product spaces. So let's look into it. Right, so proof. So what we will do is we will immediately pick a orthonormal basis. Pick an orthonormal basis of V, and let A be equal to the inner product, the matrix of T with respect to, so let's call this orthonormal basis beta of V, and A be the matrix of T with respect to beta. So we will now forget about T, and the characteristic polynomial of T is just the characteristic polynomial of A. We will focus on the characteristic polynomial of A. Now the matrix A is a matrix in our case with either real entries or complex entries, but the matrix A can also be thought of as if it is a complex inner product space, A will be having complex entries. If it is a real inner product space, A will have real entries, but nevertheless we will think about it as a matrix in the complex over the complex numbers. So the matrix A can always be thought of as a matrix with complex entries. Okay, let f of lambda be the characteristic polynomial of A, and then f of lambda will be by the fundamental theorem of algebra. This is a polynomial of degree n by the fundamental theorem of algebra. We have f of lambda splits into linear factors. We know what is the degree of f. Degree of f is equal to the dimension of V. Let's say it is n. That means it splits into lambda minus lambda 1 into lambda minus lambda 2 up to lambda minus lambda n, where lambda I are the roots of f of lambda. But what do we know about the roots of the characteristic polynomial? Where lambda I, which are the roots of the characteristic polynomial, are the same as the eigenvalues of A. Lambda I are the eigenvalues of A. But what do we know about A? We know that A is the matrix of T, which is a self-adjoint linear operator, and by one of the propositions that we wrote earlier, we know that A is self-adjoint matrix. Because A is self-adjoint, what do we know about the eigenvalues of A? We just proved that the eigenvalues of A are necessarily real. This implies that lambda I is real for all I. But what does that mean? That means that f of lambda would be just lambda minus lambda. It's going to split over the real numbers. Hence, irrespective of whether it is over complex numbers or not, f of lambda splits. So the key thing to note is that the characteristic polynomial f always splits, even in the case when it is over real numbers by the fundamental theorem of algebra. The fact that lambda 1, lambda 2 up to lambda n are all reals in the case of self-adjoint operators tells us that even if it is a real inner product space, this splits. Okay, that completes the proof. Well, this is an important theorem in the sense that when we were studying diagonalizability, many times the theorem that we proved it began this way. If you start off with a linear operator and if its characteristic polynomial splits, then we had a characterization of the diagonalizability. Yeah, so this tells us that in the case of self-adjoint operator, it always splits. So that's maybe one step towards diagonalization, but we'll come to that in due course. Let's now focus on some more properties of self-adjoint operator. So let's now look into self-adjoint operators on complex inner product spaces. But before that, let's prove one statement of linear operators on complex inner product spaces. So proposition. So let V be a complex inner product space. And T be a linear operator on V. Then T be a linear operator on V such that inner product of TV with V is 0 for all V in capital V. Then this forces T to be identically equal to the 0 linear operator. So notice that we have imposed a very specific condition of V being a complex inner product space, because in the case of real inner product spaces, this proposition is not true. So I'll leave it to you to check that. Okay, let me just note in the case of, let me just look at this, consider T to be the linear map from R2 to itself given by T of x comma y being equal to minus of y comma x, or y comma minus x, one of the two. This linear transformation does satisfy the condition that T of then inner product of TV with itself with V is always 0 for all V in capital in R2. However, T is not the 0 linear transformation here. So notice that in the case of real inner product spaces, this proposition that we just wrote is not true. This is true for complex inner product spaces. So the proof of this is going to be an identity which I will not prove. It is very similar to the identity which we had proved in one of the problem sessions last week. I'll just write down the formula. Notice that it's your job to sit down and check the inner product of TV with W. This is equal to the inner product of T V plus W comma V plus W minus the inner product of T V minus W V minus W, the whole divided by 4 plus I times inner product of T V plus IW V plus IW minus T of inner product of T of V minus IW V minus IW, the whole divided by 4. So I'll suggest that you sit down and work out this identity just like it was done in the problem session earlier. And if you have indeed worked it out, the next step is to notice that every element here, this will vanish, this will vanish, this will vanish, and this will vanish, because all of them are of the type T of u comma u, inner product of T of u comma u, and we have just put that as the condition in our hypothesis that TV comma V is 0 for all V in capital V. But that would imply that the inner product of TV with W is equal to 0 for all V comma W in capital V. But what do we know about the case when W is equal to TV? For W is equal to TV, this would imply that the inner product of TV with itself is 0 which would imply that TV is equal to 0 for all V. That means T is identically equal to 0. Okay, why did we make this observation? This observation is to give you a characterization of self-adjoint operators on complex inner product spaces. So let me write down that as the next proposition. Again, this is true only in the case when V is a complex inner product space. Let V be a complex inner product space then T is a self-adjoint operator if and only if this is a characterization TVV, inner product of TVV is a real number for all V in capital V. So maybe I should remark at this point of time that the self-adjoint operators behave like the real numbers behave in the case of complex numbers. So notice that the conjugate is being captured, the idea of conjugate is being captured by the adjoint. And what happens when the complex number z is equal to the conjugate of z is equal to z bar forces it to be real, right? So in some sense the self-adjoint operator captures the idea of real numbers in the world of complex numbers. That's the idea that is being captured by self-adjoint operators in the world of operators itself. Okay, so let's prove this proposition. The proposition here is going to use the previous theorem. The previous theorem, let's see. So what is going to be T? So if T is, so suppose T is self-adjoint, that means that T is equal to T star. T is equal to T star would imply that T minus T star is 0 and therefore this is equal to 0. But what is this? This is equal to T V comma V minus T star V comma V, and by definition this is equal to T V comma V minus V comma TV. This is equal to TV comma V minus the conjugate of TV comma V. Well, I skipped one step here. No, I didn't skip any step. So they are all in place. So this implies that inner product of TV with V is equal to the conjugate of inner product of TV with V. But that implies that this is a real number, right? That's precisely what it means for a complex number to be equal to its conjugate. So we have proved one direction. What happens if we want to go in the other direction? Suppose TVV is equal to R for all V. So this is for all V in capital V. So this is also for all V in capital V. And if you want to go in the other direction, suppose TV, inner product of TVV is in R, then that would imply that the inner product of TVV is equal to the conjugate. That would imply that this is equal to 0, and that would imply that T minus T star V is equal to, okay, so let me just not use the colors. I'll just write here that now suppose TVV is an element of R for all V in capital V. Then by going in the opposite direction above, we get that T minus T star of V comma V is equal to 0 for all V in capital V. But we are in the setup of a complex inner product space. By the previous proposition, if any linear operator satisfies the condition that TV comma V is equal to 0, then the linear operator should be 0. By the previous proposition, in this case our T is just replaced by T minus T star, t minus t star is equal to 0, which implies that t is self-adjoint. Alright, so that is one characterization of self-adjoint linear operators in complex inner product spaces. Well, there is an analog of this proposition in the case of real inner product spaces as well. We saw that in general this is not true. Let's look at what could be a analog in the case of real inner product spaces, which I will write down in the next proposition. So let T be a self-adjoint linear operator on a finite dimensional inner product space. Such that TV V inner product is 0 for all V in capital V. Then T is identically equal to 0. So notice that this proposition has already been proven in the most general setting in the case of complex inner product spaces. We don't need to impose the extra condition that T is self-adjoint. In the real inner product space, in the case of real inner product spaces, T being self-adjoint is a necessary condition to, is a sufficient condition to say that TV V equal to 0 for all V forces T to be equal to 0. Let's give a proof of this. We will assume without loss of generality that V is a real inner product space, because in the case of complex inner product spaces we have already done this. Assume that V is a real inner product space. Then I will leave it as an exercise for you to check that. Then you can check that TV comma W is just going to be equal to the inner product of T of V plus W comma V plus W minus T of V minus W comma V minus W by 4. By using the self-adjointness of T, this will follow, and the two quantities on top both are going to be 0, because that's of the type TV comma V, and that would imply that TV inner product with W is 0 for all V comma W in capital V, and by a very similar argument as earlier, this concludes that T is identically equal to the 0 vector. Okay, so let's prove maybe one or two problems. So let S comma T be self-adjoint linear operators. Then the composition ST is self-adjoint, okay, where on a finite dimensional inner product space. Let me not write it down again. ST is self-adjoint if and only if S and T commute. So let's see. So this is a proof. So suppose ST is self-adjoint. I think this, okay, let's start with, let ST be self-adjoint. Then what is going to be inner product of STV with W? And for V comma W in capital V, let's try to figure out what this is. By definition, this is going to be equal to V comma ST star of W. And we just assumed that ST is self-adjoint, and therefore this is going to be equal to V comma ST of W. But what is ST VW, if you consider it one by one, a map T acting on V and then a map S acting on V. This is just going to be inner product of TV with the adjoint of S acting on W, which is equal to TV comma SW. Since S is self-adjoint, but this is also the same as V comma T star SW, which is the same as V comma TS of W. That would imply that V comma STW is equal to V comma TSW for all V comma W in capital V. I am not talking about how we are able to conclude that STW is equal to TSW for all W. Follows by the uniqueness. This argument has been done many times, and therefore from this we will be able to conclude that this is the case, which implies that ST is equal to TS. So what is going to be STVW? This is just going to be equal to TV S star W, which is equal to V T star S star W, which is equal to V comma TSW, because both T and S are self-adjoint. But TS is equal to ST will imply that this is the inner product of V with STW. And what is this? This is just by definition inner product of V with ST star W. This would imply that ST star is equal to ST, which implies that ST is self-adjoint. That completes our proof. Okay, so let me stop here. In the next video, we will discuss what is called as the spectral theorem of normal and self-adjoint operators.